Hey guys, what is going on? This is CodedSteele, and after an extended period of laziness, I have finally decided to get back to recording videos again. So, again, I apologize for that. I've just been busy with work and all of the things that come with having a life or not having a life or whatever. So, anyways, I'm returning with an electric circuits video for you guys first today, and this is actually going to be a lab where I'm going to show you guys how to measure voltage, current, and effectively the power consumed by a circuit. So let's go ahead then and just get straight down to the results here, and then we're going to jump straight into how to measure voltage and current with an actual multimeter. So let's quickly get right into this. So we've got a 5-volt source here with a 1 kilo ohm resistor and a 2.2 kilo ohm resistor, and then finally a 3.3 kilo ohm resistor. These are all resistor values that are quite common. That is why I selected these three, as opposed to maybe doing a 1 ohm, a 2 ohm, and a 3 ohm resistor. You know, those simply are fairly uncommon. And reason being is because I don't feel like maybe I didn't cover this in previous videos, but current, although we say it's measured in amps, we typically don't run into measurements that are in the ampere region for small scale circuits. Now that's not to say, don't get me wrong, don't try to use my words against me. There are circuits that can consume amps of current, but they are few and far between. Typically, they're like air conditioning applications where you're trying to cool a house down, or heating applications like you're trying to cook food, or you're trying to run a furnace in your house, or even your Xboxes or your PS3s or your PS4s and Xbox Ones and all that stuff. They all consume amperes of current. Typically, you can look at one of the power supplies of one of those bad boys, and it probably ends up being maybe around 8 or 9 amps. Maybe not quite that high. Maybe like 6 amps, maybe, or something like that. But there is a difference between the amount of amps you're drawing on your primary side of your circuit and the amount of amps you're drawing on your secondary side of the circuit. But we're jumping way ahead of ourselves. Just understand this. Unless you're building a heating element, or you're cooking something, or straight up, you're either unless you're building a heating element, typically you're not going to run into consuming amperes of current. I can't think of any other applications off the top of my head where you would consume large amounts of current other than heating elements. That is the major one. Maybe, yeah, that's just about it. I'm going to go with that. Alright, let's move on. We're wasting too much time. Okay, so this is going to be what's defined as our ground plane down here. Ground just means that's the negative whatever. So, okay, good to go. Let's move on. How do we analyze this circuit? Well, first of all, I want to find the voltage here, the voltage here, and the voltage here. And we've discussed some principles in the previous 4 tutorials or something like that that are going to help us analyze this circuit and ultimately solve it. And we're going to apply them here today. So, what we're going to do is I've derived the equation for voltage division, which just so happens to be Vs, or not Vs, V of whatever you're testing, whatever resistor that would be, is Vs over, R1 over R1 plus R2, whatever that ends up being, your equation. So we can use this equation to ultimately solve for all of the voltage, or all of the potentials even. Potential is another word for voltage. I believe I've already talked about that. At each of these, across each of these resistors. So how do we do that ultimately? Well, this is how we're going to do it, and this is how we're going to apply this. This might not necessarily be intuitive to you guys at this moment as to how this can be applied, but I'm going to show you in just 1 second how it can be. we're going to find the voltage here on this resistor. So we're doing V of the 1 kilo ohm resistor is equal to the source voltage, which is 5 volts. So 5, that's the source voltage here. This is the variable we're solving for. Over, now it's always the resistor that you're analyzing. And I'm just going to put a 1 up here. And the reason I'm going to put a 1 and not a... Remember that this 1 kilo ohm, remember 1 kilo ohm is actually 1,000 ohms. I'm just abbreviating it with K. So I know we've taken a pretty extended pause from this stuff. So please just try to remember that 1K, 1,000 ohms. Same thing with these, 2.2, 3.3. Because I have a factor of 1,000 on in the numerator and a factor of 1,000 in the denominator, I can essentially cancel them out because 1,000 divided by 1,000 is 1. So these factors don't even come into play with the thing, and that's why I'm not going to include them in my fraction that I'm creating over here. Anyways, we do it over the total, which is this 1. Now here's the tricky part. Here is the tricky part. I have R2. I have one term here. But if we look at here, we've got 2 more resistors. Which one of these resistors do we use? Well, it's a trick question. We don't pick just one of them, we use both of them. And the reason why is because this circuit the current has 2 paths that it will travel in the circuit. And since current can take 2 paths, we have to include both of those resistors. This is a complete circuit, and this is a complete circuit. And because these are complete circuits, that means current will flow, ultimately meaning all of these elements are electrically connected. And since they're all electrically connected, we have to analyze them all together. So if you guys remember how do we deal with this? We know that voltage is the same in parallel, but it's not the same in series. So since it's the same, we actually apply our equation for parallel resistors. So we do 2.2 in parallel with 3.3. And according to my math, this ends up coming out to be 1.32. Yes, maybe. Where the heck is 1.32 at? I believe it was 1.32. I don't know if I wrote it down. I don't know. I blank on that. I don't have it written down on the sheet, evidently. So, but it's 1.32. And that would ultimately be kilo ohms is what it would be. But like I said before, we're not dealing with kilo ohms because we have factors of 1,000. So that's where now we add this term into the equation. Hopefully this makes sense to you why that works that way. Like I said, it has to deal with the fact that these are electrically connected and the current can take 2 paths. Since the current divides and takes 2 different paths, that means that these resistors are in parallel. Remember, the definition of parallel resistors is technically when current splits a path, that's when something's in parallel. Anytime the same current is traveling through an entire circuit, that's series. But if the same current is not traveling through a circuit and it splits, that means elements must be in parallel for that to happen. So that's why these 2 resistors must be added together in parallel. Alright, like I said, this, real quick, 2.2 times 3.3 over 2.2 plus 3.3. Hopefully you remember that to be the equation for that resistance stuff. And like I said, that evaluates to this, 1.32. Okay, back to this. 5 divided by 2, ooh yeah. 5 divided by 2.32, I have written down on my sheet here, comes out to be 2.16 volts. So that's the voltage here, is 2.16. So I'm going to put that right up here in this corner, right there. 2.16 kilo ohms. Beautiful. Alright, so we've got a 2.16, or kilo ohms. Wow, gosh. Volts. Volts, 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 volts. I'm going to scare away all of you guys. My bad. Volts. Alright, so Now, things get relatively easy at this point. And the reason being is because we have a 5-volt source. What do we know about a 5-volt source? Well, we know this, that all the voltages in a loop must be equal to the source. So, and we know that because of KVL, Kirchhoff's voltage law. All of the voltages must sum to, all of the voltages going around a loop must sum to 0. Ultimately, which that means is all the voltages must sum, or all the voltages excluding the source must sum to the source. So that is essentially Kirchhoff's voltage law. And since we know that the voltages here and here are the same, guess what? It becomes a second grade or third grade subtraction problem. 5 minus 2.16. Well, I think I can do that one in my head. And it comes out to be 2.84 volts. So that's the voltage here and here. Cool. So we already have one of the parameters that I was looking for in this, with this circuit stuff. So great, we're in great shape here. We got the voltages, but we don't have the currents. So now we need to solve for the currents. But that becomes an exercise in whatever the heck the phrase is. I can't think of it. But 2.16 divided by 1,000, I hope you guys will agree with me, is 2.16 milliamps, or 0.00216 amps if you so prefer. Remember, milli means 10 to the minus 3, so I'm essentially dividing by a factor of 1,000. So just keep that in mind, remember that. But I can rewrite that as milliamps because that's how we see it in the electronics world. So that is where that factor comes in. We have the I of the 1K. Now we need these two currents. Same spiels. I'm not going to, like I said, if you can do them, you can do one, you can do them all. It's so trivial at this point. 2200. And then this one comes out to be, current going through the 2200 resistor is 1.3 milliamps. And then the last one, 3.3, is 0.86 milliamps. Okay, quick check we can do to make sure we're on the right track is we can add these quantities together and see if they equate to that quantity. And you guys don't have to do this, although you can if you so prefer. I can tell you that yes, they do indeed add to 2.16. So all of these results are correct. This is a check you can do to make sure that your circuit makes electrical sense. If you're not getting the values that you put into the circuit back out of the circuit, there's a problem somewhere, clearly, because energy is not just going to, float into midair. I suppose it's given off as radiation when these things heat up, or in convection, conduction, or whatever, all those thermodynamic stuff. But not on a whiteboard, it doesn't. On a whiteboard, everything must add up to what you put it in, or what you put into it. That's just the way the world works. You put energy in, you get the same energy out. That's the way the ideal world works. So, that's, like I said, this adds up to 2.16. The last thing I want to show you guys, since now we know that that all makes sense, is we talked about power rating last time. And all I'm going to do, I'm going to use the first one for calculating the power rating for each one of these. It's the voltage across the resistor times the current across, or going through the resistor. My bad. Voltage is across, current is through. It passes through the element. So that's a day one lesson. Now, like I said, I'm not going to, it's just a simple multiplication. The voltage of the resistor times the current resistor. Well, this one's 2.16 times 0.00216. I think this comes out to be, what do we got here? 4.67 milliwatts. Power across the 2.2 is 3.7 milliwatts. And like I said, you guys can do all this math on your own. In the sake of not wasting any more time than I already have, I am simply writing the results. 2.4 milliwatts. Okay, we almost have every single thing that I wanted to calculate for this circuit calculated. There is just one thing that I'm missing at this point, and that is to calculate the total power for the circuit and make sure it matches with all of these. Like I was saying to you guys before, the total power has to be equal to whatever power you put into it. So these are the three elements that are taking up power in the circuit. They're the only three elements in the circuit that is sinking. They're sinking heat technically, but they're the only three elements in the circuit that are absorbing current. And since they're the only three elements that are absorbing current, that means that if we add all of them together, that is going to be the total power. So, if we add all of these values together, we get the total power to be equal to 10.8 milliwatts. So cool enough, and here's where things get really cool. Remember how we check the current? And like I said, we can check the current, we can check the voltage, we can check all that stuff. We can check the voltage just by adding these two numbers together, making sure we get 5. We do get 5, good. You can add these numbers together, make sure you get the total current going through the circuit, and we do, so we know we're good. You can do the same thing with the power. We can calculate the power and make sure that it matches this value. How do we do that? Well, it's actually very, very simple. The power supplied, or the power total, since I labeled it that way, must be equal to the voltage applied total times the total current applied. Very, very simple. So, what is the total voltage? Well, that's this. That's 5 volts. So that's the 5. But what is the total current? Now, that one, you kind of have to think about a little bit. What did I say the total current was? Remember that, well, I'm just going to give it away. This is the total current. Reason being, remember what I said about elements. All the current must go through the circuit and then ultimately return to ground. So it flows this way and then it flows back to ground. Or it flows to ground, whatever. So all of the current must flow in a path, but when it reaches a break in the path, it splits and takes those two different directions, depending on which one has the least, whichever one has the least amount of resistance is the path that more of the current is going to take. So, but like I said, we've already discussed that too. So since, like I was saying, the reason this is it is because the current doesn't split until it gets to this path. So up until this point, all of the current must pass through the 1 kilo ohm resistor, every single bit of it. Not a single milliamp of current, microamp, nanoamp, picoamp, femtoamp, not a single unit of an amp can bypass this resistor because it's the only path that it can take. So, knowing that, I can take this 2.16 milliamps that I had before, and I hope you guys see that 5 times 2.16 gives me this. So we are good to go. We're all checked out. Everything makes sense. Mathematically, physically, electrically, everything checked out for us. So let's go blow some resistors up. I will see you guys over at the bench. Alright guys, here we are over at the bench over here. And I have a simple circuit wired up, which is the exact circuit that we did on the board. I have a 1 kilo ohm resistor right here. I have a 2.2K resistor right here. And I have a 3.3K resistor right here. You guys may see the colored bands on each of the resistors. That is how you determine what value a resistor is. So, just so you guys are aware of that, we'll probably cover the bands and the multipliers in a later episode and maybe another lab video that we do. But for this one right here, just trust me, that's a 1K, 2.2K, 3.3K. And like I said, you can tell that by the colored bands. Alright, cool enough. That's good enough of an intro on this thing. Let's actually measure some of our parameters. So I calculated that we should have I know that looks like weirdness going on, but that's 2.16 right there. So I calculated 2.16 across the 1 kilo ohm resistor. If you guys watch the meter, hopefully this video comes out well. You guys can see I get if it will stay still for me and not be stupid. You guys can see I have 2.2 on the meter. We'll discuss why it's not exactly what I calculated here in a minute, but understand, okay, that's extremely close, all right? That's probably, my circuit can probably tolerate that. It's not that big of a deal. So 2.16, 2.2, you know, pretty close. And then we can assume that I have 5 volts applied over here on the source. We can assume that 5 minus that 2.2 is going to be what's here, and we shall see if that is true. If it'll ever measure for me. Please measure. What the heck am I doing here? Come on. There we go, 2.9. Okay, so this source is probably dialing in at about 5.1, about-ish. I'm assuming that's probably what it's at. I can check my meter. Yep, 5.1. So 2.2 plus 2.9, 5.1 is what this meter is saying. So, like I said, pretty close to 5 volts, but there are tolerances in this world, and you know, that's just what we're going to have to deal with. So we measured the voltage simply by, you guys saw what I was doing, taking this probe, putting it here, and putting it there. That's how you measure the voltage across a resistor, is you put the 2 leads across, like that. But there's another parameter we have to measure. Remember, guys, we have to measure the current. In order to measure the current, it's a little different what you actually have to go through. You actually have to take the circuit and break it up. So I actually have to take this, and then I have to put it in current mode. And yep, we're in the right, still in the right leads there. So let me quick grab these leads over here for plugging this stuff in. Should have been ready for this before I started recording, but you live and you learn. So quickly, let's get one of these, 2 of these little IC probes, which make awesome little dealios for, you know, doing stuff with the circuit. So like I said, we're measuring current. So to measure current, I take my red lead and I hook it up to this first resistor right here, and it snaps away because it's being difficult with me. Please don't do that. Okay. And then I take the other black lead and I hook that up. Come on, any day now. Why is this being difficult? Okay. Alright, and then I hook that lead up to here. 2.25 milliamps before the lead snapped away on me because it's being bogus. And then now my breadboard's full. Alright, quickly look at the thing. 2.25. Okay, cool. I calculated 2.16. That's pretty close. You guys get the point, hopefully, at this time that I can just split the or take one of the resistor legs out and then connect it to the node, which is essentially connecting it to this point in the circuit. I break one of these connections, I put one of the test leads here and the other test lead there, and I can measure the current going through that resistor. I could do the same thing with the 2.2 and the 3.3, and what I would find out is it's very, very close to what I calculated. We calculated, or we had measured right now just 2.25 going through the circuit. I have calculated out 2.16. So now we need to talk about the difference. Why did this come out 2.16 and not what you would expect? Why did it not come out, or why did it come? Why did we calculate 2.16 and get 2.25 on the meter? Well, we have to talk about tolerances. And this is essentially the thing of all electronics. We don't live in a perfect world, right? Hopefully that makes sense to you guys. You know, all kinds of crazy stuff happens every day. We are far from living in a perfect world. So since we don't live in a perfect world, the power supply I'm using is not perfect. It's now outputting 5 volts exactly. We saw it's outputting 5.1. So it's outputting a little higher voltage than it's supposed to. I could probably dial it in a little more precisely and possibly target it right on 5 and maybe get even closer to that value. But I probably still won't get exactly 2.16. And the reason is because of, like I said, tolerances. The meter has a tolerance. The multimeter has a tolerance. The leads have a resistance. These leads, albeit they have probably a very low resistance, these leads are a resistor. And these leads have a resistance, if this thing will tell me, of it said 0.4 ohms. Just trust me on that because it's being very slow in dialing in. But it said 0.4 ohms on there. So we add that 0.4 ohms into the circuit. It gets all these resistances add up. The power supply leads here have resistances. These IC leads have resistances. So all of that stuff is interfering with our measurements ultimately and changing, voltages is at certain points and currents at certain points. So, like I said, these are the tolerances we have to live with. So we have to often accept that what we calculate is not going to be exactly what we expect. So like I said, we have to calculate for a percent tolerance. So oftentimes you'll see that on a chip. The chip will say anywhere from 2.5 to 5.5 volts or something like that, or it'll say it operates from 3 to 6 volts or some weird stuff like that. You're going to see that stuff. Why they do that is because of the fact that if somebody wants to drive this thing at a higher voltage, maybe to get a better, stronger signal out, so they want to drive it at 5.5 volts or something, if their power supply all of a sudden decides it wants to be, if they read out 5, but they're outputting 6, or they're outputting 5.7 or 5.8, that extra padding needs to be there in order for them not to blow their circuit up or blow their IC up, because it's not, well, I shouldn't say it's not fun blowing stuff up, because I like blowing stuff up myself. But we ultimately want something to function, and if we don't, if we're not careful and we don't create tolerances in circuits and whatever else, we don't often, get what we expect. I'm going to give you guys an example of a tolerance right now. I work for a transformer monitoring company, all right? So I work on top of these big industrial-sized transformers that are really big, 500 plus kV, 750 kV transformers. And these transformers vary, on the amount of power consumption. There's a certain amount of people in a general population, and they go ahead and they, loads change different times a day. Your wall voltage coming out of there is supposed to be 120. Well, depending on the time of day, it could be 110, 105. It can move all over the place. That is a tolerance. Manufacturers have to spec your TVs and your Xboxes and your sound systems to be able to run from a certain range, say maybe 90 volts to 130 volts or 140 volts or something like that. Just in case, the load goes down, it has to be able to tolerate the spike in voltage. And if the load goes up, it has to be able to tolerate a drop or reduction in voltage. And we'll talk about loading effects later. That's something for a way later time. But essentially, as I was saying, we live in a world with tolerances, and ultimately we just have to deal with that stuff. So, you know what? I'm bored. Let's blow up resistors. Let's see. What resistor can I tolerate to lose? I have a ton of 300 ohm resistors. Yeah, let's blow up a 300 ohm resistor. Yeah. So, remember what I was talking about with power ratings before in a circuit. So if we exceed the power rating of something, it does bad things. So I'm going to show you what bad thing it does. So where'd my 300 ohm resistor go? Orange, black, brown. That should be 300. Yeah, that's it. So this is a 1/4 watt resistor right here, through-hole resistor right here. And if we apply a voltage greater than what it can tolerate, it will blow up. So that voltage should be, let's figure out what it is, and I will try to drive it to that point, if I can even drive it to that point. Let's see, 300 times 0.25, and then take the square root of that value. 8.6. So what we're seeing is around 9 volts, this thing should give up the ghost. So let's see if that happens. So we should see right around 9 volts. This thing should start. It's getting warm, guys. We're probably straddling its threshold right now. If I up it another volt or two, yeah, these leads are getting very hot. So it's starting to. I have just upped this supply to its maximum, which is 15.5 volts. Oh gosh, that thing's getting so incredibly hot. So the power rating right now is probably past what it's supposed to be able to tolerate. And this is a stubborn guy. Right now we've got, is that 15.5 squared, and then divide that by 300. Right now we're putting almost a watt across that thing, and it's not even budging. What a stubborn thing. But like I said, we live in a world of tolerances. So although this is a 1/4 watt resistor, it doesn't mean that it can't handle more than a 1/4 watt across it. And this thing's definitely, very toasty. It's very hot to the touch, and probably another volt or two. And I would say for sure it would give up its ghost at that point, because this is not a watt rated resistor. Like I said, this is a 1/4 watt, so probably not good for. It's not even good for it to be this high. And the reason, like I said, we spec it that way is because it's small. We try to suppress the amount of power across it. Anyways, I'm rambling at this point. We got to see kind of, what happens when we, screw with circuits and whatever else. Unfortunately, we didn't get to see a resistor blow up. I could have put a 0 ohm in there and possibly blew it up, but I don't have a lot of 0 ohms or 1.5 ohm resistors, so I know those would definitely blow up, but I don't have a lot of those on hand at the moment. That's why I wasn't willing to risk losing them. But anyways, that's all I have for you guys for this tutorial. Please like, comment, subscribe, and I will see you in your next electric circuits video.